to listen to me talk about fakes. This is wonderful. Thank you very much for coming. Our last day of TechEd together, I've had a great time here. Hopefully you have had also a good TechEd this year. So this morning, I'm going to be going into a deep dive on Visual Studio 2012 fakes. And if you've been to some of my other talks, I've done a little touching here and there just to show a little bit, hopefully get some interest. And today I'm going to show you some scary parts, the good stuff, the evil stuff. But I am going to be doing a lot of coding. I'll just tell you now. And I'm going to be playing around with some strange things in code. And it's not, I've got some slides, but I just want to give everybody, we're going to be digging around because I want you to understand all of the crazy things that you can do with it, and also how you can understand some of the internals of it, which means you can then be even more powerful with it. It is an amazingly powerful tool. And as I like to say, with great power comes great responsibility. So let me just also say one thing. It's actually, even though it's a pretty big room, it's a nice sized group. So if you have questions, don't be afraid to raise your hand. I'll call on you and I'll repeat the question back for the recording and we'll have a good time. Okay? So just don't be afraid to ask questions. Put your hand up. So you guys have probably seen me do this kind of a thing before. The kind of overarching statement that I want everybody to understand here. I am a very strong believer in unit testing. Unit testing is testing the smallest thing that you can test in isolation from other things. And depending on your code, that might not be very small. When you read the books on unit testing and you hear the Agilistas talk about TDD and all of those kinds of things, they talk about very small things. But that requires you to have designed for that. And if you have not, then it is going to be bigger. And I have seen people where the smallest thing that they can test in isolation is the entire app. So maybe for them that's a unit test, but that hurts. That hurts. And so when we have legacy code, we have systems with thousands of lines of code that was never unit tested before. I've had people say to me, it's impossible to unit test that the way that you want me to, Peter. And sometimes the answer has been, yeah, probably it might be. You're going to have to change the code. But it doesn't have to be. Untestable code or hard to test code comes from a lot of places. It comes from a lot of reasons. I have been lately calling it get her done code, from an American kind of euphemism for, just get her done, right? Just drive through, don't worry about it. Expediency. The deadline is looming. You must finish it. Don't worry about how you build it. Just build it. And we do a lot of bad things when we're coding like that. We put code in the code behind. We create lots of crazy, weird dependencies. We don't inject the dependencies, so they're not replaceable. There's a lot of things we do that aren't very good. Mix up our database logic. That's a famous one that we all love to do. Right? You double-click on the button, you get to the code bind handler, and you call up a SQL connection. Yeah, have fun testing that. These monolithic, highly coupled designs are notoriously hard to test. There's a lot of things that you can see when you look at a body of code to help you identify that it's going to have a problem from a testing perspective, from a unit testing perspective. If you try to write tests and you end up with complex setup and teardown, and it's difficult to write the test and you end up with huge amounts of code at the beginning, before you can even say, do something, that's an indication of a hard-to-test system. And the kinds of things that are hiding in there are often environmental dependencies. So the application is making direct calls on the environment without any abstraction layer. And making those go away is very problematic. Static methods are often challenging. Hidden object creation is what I call when inside of a method you just start newing things up. And I'll show you some interesting examples of that from real code. And then complex external frameworks. SharePoint and others can make it very difficult to create tested systems. So I'd say any system where the tests require complex setup or where the tests run very slowly is almost an untestable system. You're able to test it, but what happens is when your tests are very slow, very brittle, they break every time you change the code, what happens? We stop caring about them, we stop running them, we stop writing new ones, and eventually we really are truly untestable because we don't bother. So when we think about test setup, sometimes we think of, the attribute, right? Test fixture setup and those kinds of things that we have in the various frameworks. And sometimes it's a little sneaky where they come from. I mean, you look at this method here, and if we wanted to test this method, we could write a test like this. Looks like a reasonable test. It's not complicated. It's not too bad. The problem we have is that line there. File.readAllText from an external file is forcing us to do this setup. And what's the problem here? This is directly dependent on our environment. What happens if I'm on a server where I'm on a build server and I don't have permissions to write to the disk in whatever the current directory is? Do we even know what the directory is? Does the test have any control over what the directory is? Well, he doesn't right now. This is a very simple example that doesn't look like complex setup, but in fact, this is a challenging system to test in a very reliable and dependable way. One of the most simple examples I can find. But there are also environmental dependencies, and you might have seen me show this one on Wednesday. So some of us are old enough to remember the Y2K, and so here we have a check that says if datetime.now equals 2000 January 1st, throw the exception. Testing this is problematic. Maybe we do it like this. All right, that's a good test. At the end of it, your build server's messed up. And maybe I have permission to make this call on the build server. Probably not, though. Right? We'll just change the system time. I've seen people write tests like this in the real world. Not good stuff. So the essence to doing good unit testing, then, is isolation. Is creating isolation from the thing we want to test, the thing we want to verify, and as many of its external dependencies as possible. Remember, my definition of unit test is the smallest thing that I can test in isolation. So therefore, isolation is critical. And understanding how to do isolation and how to set that up is very important. So when we have these tests with complicated setup, we have non-deterministic results, we have untestable code, we're going to be in a very difficult situation, and we may not be able to isolate. We may have to come up with other approaches, and I'll be covering some of those. And we really have two choices for isolation. We can design for isolation, a testable design with abstraction layers and interfaces, dependency injection. We're going to use stubs and mocks. We're going to use overrides. This is a system that is going to be easy to test. It's going to be flexible. It's going to be modular. We may have an untestable design, however. No abstraction layers, monolithic, lots of static methods and internal object creation, sealed types. Sealed types are famously difficult to test because you can't derive from them. You can't use Liskov substitution and all these other things to make replacements. So I want to just stop really quickly and talk about this. A couple of us were talking about this last night at the Ask the Experts beer drinking. It wasn't really a dinner. So there are these 5 principles that Robert Martin started talking about back in the 90s, early 90s, that we kind of think of as being the 5 principles of good software design. And you might wonder why I'm bringing them up in this talk. But if we take a look at these, single responsibility, there's never more than one reason for a class to change. That's actually a much better definition than most of the others I've ever seen. A lot of people think it does one thing and it does one thing well. Well, but how do you know it does one thing? You know it does one thing when there's only ever one reason I need to change it. That's a pretty good one. The open and closed principle is a little bit different, but it's the idea that you should be able to extend it, but without changing it. Liskov substitution says if I take a derivative of a type and pass it to somebody who expects the original, it should work. Interface segregation. Many small interfaces is better than one gigantic one. And then dependency inversion. Always depend upon abstractions and not upon concrete things. And the reason I bring this up is because over the years we've discovered a very interesting thing. Well-designed software conforms to these 5 principles. And if you conform to these 5 principles, your software is easy to test. It's interesting. We get it for free. This is why they say if it's easy to test, it's well designed. Because you're all stuck in this cycle here. Because if it's easy to test, it's solid. Therefore, it's well designed. And so we get all of this stuff coming together. So think about these solid principles and think about it in your code when you're putting things together. So before I get into the evil, the good stuff, the evil stuff, we have to start by looking at how do we do this the right way? Let's cross this one off the list. It'll only take us about 5 minutes to get it done. If we have a system that has one of these dependencies, it has one of these bits of code that is very challenging for us to test, has an environmental dependency, for example. The easiest thing for us to do to help move towards a solid design and move towards testability is to refactor to interfaces. So we replace those external calls with interfaces, we encapsulate them up, we take them out of the object in question, and now we have a slice, we have a layer, an injection point where we can provide an alternative implementation, provide a replacement, and get inside and change that code. So we wrap up these external APIs. What's really nice about that is then the code we're testing has right in its signature an expression of its dependencies. Might be on the constructor, might be on the method parameters, but you know exactly what it depends on because the parameters tell you that. There's no questions. You don't have to wonder, does this maybe depend on date time somewhere down on the inside? Because we can just read it on the signature. And there's some interesting patterns we use when we do interface segregation like this. The null object pattern is when you provide an implementation of the interface that does nothing. It's very useful. Instead of putting in null. Putting in null, now you have to have all kinds of checks in the code. So instead, put in a null object. The code can happily consume the interface, and it just does nothing. A default implementation is similar, but basically it says if you don't provide it at all, use this one. And then there are various dependency injection or inversion of control frameworks that we can use so that we don't even have to submit them. The class expresses its requirements and the container fulfills. Now, refactoring interfaces has some of its own challenges. And so we're just going to have a quick peek at some code. And then we will get into the evil part of fakes, the good part. It's funny, I say good and evil at the same time, like they're together. So in the slide a minute ago, I showed you the code on the left. So we have this throw if end of the world, datetime.now equals new datetime 2000 January 1st, throw the exception. And on the right there is that test, and this is a terrible test. We know this. We don't like it at all, so I'm going to get rid of it. And instead we need to think about what do we really want to do here? How would we like to test this? And I find sometimes when I want to ask this question that I'll start by actually writing the test I would like to have, because this will make my life better. It helps me guide what I want to do over there. So we know that we have this end of world checker class, and we know that we have this throw if end of world. Well, what if instead of just calling it with no parameters, I'm going to pass in something? Okay? And maybe what we're going to pass in is a current time provider. Okay? So we know we want to change the signature to be like this. So I'm going to go over here and I'm going to create a new method that implements this type. Okay? We'll leave the old one alone for just a minute. Because I'm refactoring in place, I don't want to change the existing system quite yet, because I will break everybody else who depends on it. So I'm just going to add a new one. And this now needs to depend on an I current time provider. This is going to get a lot easier for us now. So because what we can say, let me go allow Visual Studio to make this interface for me. What we're going to say now is, instead of if datetime.now, these two lines up here, we're going to ask for the datetime provider to do it. So if the current time provider dot now equals new datetime 2011, then throw. Okay, that's good. Now we don't have that method, so we'll let Visual Studio make that. And let's go take a look at what our interface looks like now. Okay, so here we are, our current time provider. I'm going to make a few adjustments here for visibility. We'll make that public. We'll make that public. Excellent. And this is not a class, but an interface. Okay, so far so good. Okay? So we've now adjusted the class. Now, when I'm using Visual Studio Fakes, I create the fake assemblies directly from the references in the Solution Explorer. So I have in my testing project over here, I have a reference from I don't? Good. We'll add a reference then. We're going to add a reference over to the other project in the solution. Okay? Oh, I'm going the other way. My mistake. So in our references down here, you can see we have a reference up to the system under test, which contains our code. Now, in order for me to create fake types for this, I right-click on the reference and I say Add Fakes Assembly. Now, what happens behind the scenes is Visual Studio makes sure that all the projects are built. It runs reflective paths over the target assembly. It generates a new assembly and adds a reference to it. That new assembly contains stub types. Stubs are concrete implementations of the interfaces that it finds. And I can then use those very easily. And you can see here's the new reference, system under test.fakes. So now inside of my test method, I have a thing called stub I current time provider. And we'll let Visual Studio. Let's do this. System under test dot fakes dot. My interface is what? Yes, thank you. So I love coding with help. It's like pair programming in a team room. We're all together. It's wonderful. There we go. So that actually points out a very good thing, right? The generated assembly did not contain a stub for the type I changed because the target assembly did not compile. I've recompiled the target assembly. We will automatically regenerate the stubs assembly. So when the target changes, the stubs assembly will regenerate automatically. And if it doesn't change, it won't. So we're only building things we have to build. This is good. Now we'll try again. Stub I current time provider. And there it is. Now I want to point out a couple things about the conventions here. The type I current time provider lives in the namespace system under test. So the stubs for it will live in that same namespace .fakes. There's always a convention for where you can find the things you expect to find. Okay? So I'll new one of those up. Okay? Make this a little bigger. Okay, so there we are. We now have our stub. Now, the stub needs to have an implementation of the interface method. We do this with a simple assignment. There's the method. Okay? And we provided a delegate. Okay? So what that's going to do is that's going to become the implementation, become the body of the method in the concrete class that derives from my current time provider. Simple stuff. Of course, it's not called that now. It's called stub. Okay? And we now need to confirm this by running an expected exception. Okay. So now we should be able to build this. And check our tests. Green light pass, good. Now, a couple of things I want to point out about this. If you've been in my other sessions, you'll hear a little bit of repeat here, but we intentionally did not create a new language for you to learn. You know, dot returns and dot setup and all these other things. We're using standard language notation. So this is a lambda expression being assigned to a delegate. Now, if you would prefer to shorten this a bit, you can use the initializer syntax that we have in C#, and you can make it look like this. It's the same. And now it's all in one construct. So now I'm newing up the current time provider and setting the property delegate all at the same time, all in one shot. All right. So this works. And we are now able to fill that in. Now, we still have a bit of a problem. We have some duplication over here that we don't like. So now I want to show you that pattern I talked about of the default implementation. And what we really would like to do here is we want to get rid of this, because this was the dependency that we didn't like. And instead, we want to call the other one. So I'm going to just call into the other one. And I'm going to provide a new default current time provider. Now, that type doesn't exist yet. And since it's going to be a default implementation that is only ever used right here, I'm going to implement it right here. Okay? And here is now where I can introduce and now I have it all cleaned up. Code that continues to call the old system with no constructor parameters will work. Code that is able to do the providing the new interface is happy. Now what we would like to do is start to go find those places and get rid of them. And if we were using a dependency injection container, we would express a class like this one, like this default one, via the dependency injection container, and everybody would then happily work. But again, if you look at this method here, throw if end of the world, it's very clear what its external dependencies are. There's nothing hidden anymore. So here we have now the stubs component of fakes. Fakes has these two parts, stubs and shims. Stubs are concrete implementations of interfaces, and we use them very simply. And when we're refactoring to interfaces, or if we're doing test-driven development or other patterns where we are often using interfaces intentionally, they're very easy to use, and they're very fast. Very, very fast. Because they are compiled in advance, and because we're using all language constructs built right in. Yes, sir?
You said, if I were to use an injection provider, why would you not?
So the question was, why would I not use a dependency injection container? Why would I choose not to? That's really a philosophical question, to be completely honest. I know people who just don't like them. They would rather do it themselves. They feel more comfortable providing dependency resolution themselves. I have recently been doing a lot of exploration of Ninject, which is one of the frameworks we have in .NET. And I like it. It's simple. It's fast. It works well. Other people like to use Unity, which is from the Patterns and Practices team. In fact, I wrote the core little piece in the center of Unity 7 years ago that later became Unity. So there's a lot of ways to do it. They are very nice. They do have their own challenges that I'll talk about in a little bit. Okay. Jump back over here. Like I said, I didn't want to spend too much time on the simple one, because if you've done mocking before, if you've used stubs before and interface segregation type things, you're familiar with this. There's not too much to show there except the basic structure of how it works. Now, there are some good things about refactoring to interfaces. The code expresses its requirements. I talked about that. We become very loosely coupled, and we get that free gift of the substitution, the substitutability. And we can replace it. Maybe we don't want to use datetime.now anymore. Maybe for whatever reason we've slid to a platform where there's a different way for us to get the current time. And our classes become much more cohesive. Cohesive is that single-mindedness. It does one thing when you do this correctly. But there are a couple of dangers you have to watch out for. One is a thing I call dependency addiction. This is when you have a class who suddenly has 6, 7, 8, 9, 10 interfaces that it depends on. And in fact, this is why people get nervous about dependency injection containers. And it's also why they get nervous about auto-mocking containers. Because both of those allow me to suddenly build up this explosion of dependencies via interfaces, and it always seems to just work. Isn't that great? Except if I have a class that has 10 external interface dependencies, it is probably not cohesive. It does not do one thing. It does 14 things. And this is a concern from a design perspective. And this, of course, type explosion is all of these interfaces coming into being. That bothers some people. Doesn't bother me, but everybody's got to have their own way. And it can be a bit expensive. I mean, there's the time involved and the disruption involved in your code base of going through and introducing all these interfaces and having the overridden methods and all these other things. And you may not like that. I think in the end, it does produce better code, but everybody has to make that decision for themselves, what they like in their code and what they don't. So when we have these interface dependencies, stubs and mocks are a very natural way for us to do it. And using the Visual Studio stubs that I just showed you gets us that. If you've used MOQ or NMock or Rhino, it should be very familiar. Now, one thing that those frameworks provide, and you'll notice that I do not call ours Visual Studio mocks. I make that distinction because a mocking framework provides the ability to do that verify thing. If you've used MOQ, anybody? Hands? Yes? MOQ or Rhino or NMock? Okay, yeah, their hands are bouncing. So everybody's used one. That verify thing, that set up and then verify, right now the stubs do not have this capability. I'll show you at the end some things you might be able to do to get that. And we're looking at it too. So stubs are generated at compile time. They run very, very fast. It's natural language features, and they are type compatible with the interface. So I went ahead and combined those two demos because I wanted to have something for you extra at the end that's fun. So I just went ahead and showed you the extract interface and the stubs all at one time. OK. So let's jump to here. There are always going to be cases that you're going to run into where you cannot refactor to interfaces. You may have a situation where your class is required to derive from something that is problematic. If you work in SharePoint, you already know exactly what I'm talking about. Your web part must derive from SP part. And SP part does a lot of crazy, ugly things in its static constructor about bringing up HTTP contexts and web requests and all these other things. Testing in that world is very, very painful. You may also have a situation where the only way that the object can really be used in a sensible way is within this complex graph of objects. You have to have all of these things all come together. And there's a lot of places where this occurs if we're doing anything in the web. We get HTTP requests and request messages and response messages and all these things. And it all has to be there in one way or another. And of course, we may just decide we don't have time. The expediency issue may come to bear. The deadline is coming. The boss is pissed. We've got to deliver. And finally, and I have seen this one, I have seen teams who do not believe in using interfaces. We don't do that. So they have an interesting challenge. The substitutability problem is very, very in their face. So I've written a little bit about this on my blog and in other places. It's a thing I call the catch-22 of refactoring to interfaces. Catch-22, of course, was a book by Joseph Heller that was describing this interesting problem of a soldier who didn't want to go fight. And so he thought he was trying to express that he was insane, except they said, no, if you wanted to go fight, you would be insane. And since you don't want to go fight, you're not insane. And he would get stuck in this loop of, am I insane, or do I need to go fight, or should I want to go fight, or do I not go fight, back and forth. And he couldn't get out of the loop, and so he had to go fight, even though he was insane. In the Agile world, when we have had people come up to us, and I've been doing this for years, and people come up and say, so I have this system, and I can't test it. I can't unit test it well. How do I do it? And we would always say, well, refactor the code so that you can test it. If you look in this book here, Martin Fowler's book about refactoring, the canonical guide to refactoring, he says, It is a disciplined technique for restructuring an existing body of code, altering its internal structure without changing its external behavior. When you look elsewhere in the book, he is very clear about how you know if you changed its external behavior. You have unit tests. So I'm telling you to refactor the code, but you're telling me you can't write unit tests. Well, I'm not allowed to refactor because I don't have unit tests, but I can't write unit tests because I need to refactor. Catch-22. It turns out shims are a marvelous way to get out of this problem. So I'm going to show you some examples of using shims with real code. And I call this isolating the brute force way. This is forcing the change. So if we go back to the code we had before, I'm going to start with a simple example, and then we will go to a much more complicated one. But the simple one always gives us a good start. I'm going to go and change our checker, our end-of-the-world checker, back to what it was. Okay, we're going to take this return datetime.now. We're going to put it right here. Okay, we will then get rid of that. Little tidying. Okay, so if we were back here, of course my unit tests are going to fail to compile, but we'll get there in a second. So we're back here now. The datetime.now is the problem. I will fix the test because it would not going to let me build. Okay, now we can build. The datetime.now is the problem. We would like to be able to make datetime.now do something else. This is where we come to shims. And shims are a way of detouring, intercepting, and rerouting to a new place any call in .NET. So how do we do that? Datetime lives in the system assembly. So I will go in my unit tests, and I will find system, and I will add a fakes assembly for system. This one takes just a little bit longer than that other one, because it has more things to do. It turns out the system reference is actually two assemblies. It is MS-corelib, and it is system DLL. And if we keep an eye here, eventually they will both appear. There it is. MS-corelib is here, and system is here. Now that those exist, we have the opportunity to use shims to get in the way and intercept. The naming convention is similar from with stubs, except now it's shim some type. So I'm going to say shim date time. And you can see the namespace is, again, what we expected. It's in system.fakes, because the type is in system. We'll let him bring in that namespace for me. Yes. Now, when we talk to the shim date time, we're talking to something that looks very similar to the real date time. So since the now property is a static property, then the replacement for it is also going to be a static. So we just go ahead and hit dot. Now. Now you'll see it says it's called now get. And it's called now get because, of course, every property in .NET has two parts. The get method and the set method, if you look in the IL code. And we want to replace the getter. So I'm going to do this. Well, again, I'll use the lambda expression syntax. Nope. Stop it. Sometimes the IntelliSense makes me crazy. Okay. So what is this going to do? This is basically saying anytime anyone in this app domain for the rest of time calls datetime.now, calls the getter of datetime.now. It will not use the built-in implementation, but will instead use this implementation. So notice a few things I said there. In this app domain for the rest of time. This could be a problem. I mean, our test runner probably uses datetime.now in order to put the start time and the end time on the tests. This probably isn't what we mean. And if I try to run this test now, it will actually fail. And it will fail because we do not let you do a shim without providing a scoping region. So I'll do a scoping region very quickly. And we do this with a simple using directive, like that. And this just tells the system where this replacement is valid. So let me tell you a little bit about what really is happening here. When you run your tests, we use a modified version of the IntelliTrace profiler. And we can attach the profiler to the test running process while it's running. And every method that gets called is offered to the profiler. It says, hey, do you want to play with this one? And now for datetime now get, we say yes. We replace the call, and we instead put that delegate expression in. And every single method call gets affected by this. And the using directive, this bounding region, tells that profiler when to turn on and off. And when it hits the end, it clears and removes everything that has been previously installed. Okay? So now that we have done that, we should be able to simply call our system under test. End of world checker, dot throw if end of world, like that. And we should get our exception, which means our test should pass. Okay. Now, do you notice it's a slower test, right? It's 89 milliseconds now instead of 15 or less. And again, this is because we're using the profiler. These tests are slower. Be aware of that. They cannot run as fast as straight-up .NET code that's been unmodified by the profiler. And that's okay. So there's a simple example to give us some sense of what it looks like in structure. Now let's look at some crazy things, because that's why we're here. So I want to show you a system that I've been working on. I've used this in a few demos, but I haven't shown you this part of it. So you have not seen this ugly little bit before. Let me first explain to you what this application does. Make these extra toolbars go away. Okay. So if I take this application and run it, what it does is it reaches out to a web service, downloads all of the earthquake data from the United States Geological Survey, and presents it on a map. And here I am with my map, and we can see all of the earthquakes. And we can see the most recent one was in Tajikistan, right there, 4.7, and it happened at 4 o'clock in the morning. Okay. So this is what it does. And when I designed this app, I used model view model, right, which is a pattern of separation of concerns. This is a good thing. This helps us keep our things separated and testable. So my code should be very nice and easy to test. Except, I did some bad things. So I started off fine. But if you look down here at the bottom, you see this little timer down here? Use the other one, that one. This little timer is counting away. The way I implemented this perhaps was not so smart from a testing perspective. But it felt good when I was writing it, so it was fine. Or was it? Now, the code for this lives in my view model. And if we take a look at the implementation of this method, start timer. Okay? So on line 42, I call refresh data, which reaches out to that service, pulls back the data, transforms it, and pushes it into the view model so the map and everything updates. Then we knew a dispatch timer object, a new one up. Dispatch timer is a background processing thread timer, runs on a tick. And then I attach to the tick method, to the tick event handler, an anonymous delegate. Takes the sender and event args, and what does it do? It starts updating that message every tick, every second. But it's also counting, and when it gets to 30, it calls back to the refresh data again. So my message is updating every second, and my refresh data happens every 30 seconds. And then these line 55 and 60 turn it on. That looks like good code. Pretty simple, easy to read, easy to understand, and very, very, very difficult to test. There's a bunch of things I might want to test here. I might want to test that the refresh data gets called only after 30 seconds. And that it doesn't get called at the very, or that it gets called once at the beginning. I might want to check that the message gets updated every second. There's a bunch of things this small block of code does, about 5 things. So if we wanted to confirm, for example, that that the message here gets set every time through the cycle, how would we write a test for that? Because this is happening inside of that dispatch timer that has been newed up for us. Let me show you. So I'm going to go over to tests. I'll go to the bottom and we'll start writing a new test. Okay, we know we have to use a shim. We have this hidden object. This object is embedded inside of this other method. In fact, it's embedded within an anonymous delegate within another method, even worse. So we're going to want to have a shim's context then. And I will tell you, my recommendation is always to do this shim's context create within your test method. Resist the desire to pull it out into a setup. Because you don't know what happens between each test call in the test runner framework. And if you leave that those changes installed, they will persist across all of the tests and across those framework runs. You don't want that. So we're going to do that. Now, the dispatch timer lives in one of the WPF assemblies. I have already added a shim for it, or a fakes assembly for it, and it is in here as Windows base.fakes. That's where that guy lives. So that means I can now say shim dispatch timer, shim dispatcher timer. There it is. Now, remember, inside of that code, it newed up. It created a new instance. It's not static, so I'm going to have to figure out how to replace the one he later creates. Well, we have a way of doing that when we go to this all instances. All instances says all future instances. Any occurrence of dispatcher timer anywhere is going to now have this override, regardless of where it comes from. And I'm going to take over his tick. Now remember, tick is like a property, which means it really has two methods hiding on it. It's because it's an event, it has add and remove. I need to take the add. All right? And it's going to, because it's an instance method, it always has one argument that is the this pointer. You know, your this when you're inside of the method code. And I'll just call it instance. And then it also gets past the handler itself. That's the attachment that we put our delegate onto. We're going to assign that now. Now what I would like to do is I'd like to collect the method, the delegate, that delegate, anonymous delegate that we have in our code. We want to collect that so we can use it. We're going to treat it like a function pointer and collect it. So let's call it tick. No. Okay. So what this did is it took the handler that was passed into the add method and stored it into a local variable. Well, I have to declare that variable. It turns out it is event handler. Okay. So at this point, what I've done is I've collected that handler and I have it. Now I can call it as if the dispatch timer had called it. So what I'm going to do is in my test, I'm going to pretend to be the timer. And I can call this method now exactly as if the timer had called it. Does that make sense? So if I were to do this, tick. That is exactly as if the timer had ticked once. But I have another problem, right? That code called start. So it's actually going to spin up a timer. I don't want him to do that. So I will take over that one too. Start. And start takes no parameters, so it's a lambda expression of nothing. And I'm going to say do nothing. Oh, maybe he doesn't take nothing. Start. Oh, it's an instance method. So, because it's an instance method, it always has to have the this pointer. I keep forgetting this part. Okay, so what this says is now the start method does nothing. But I got the handler. Excellent. So now we can pump it. We can do whatever we want. Right? So what we're going to do now is create an instance of the main page view model. Okay, here's our new view model. It needs a repository. I used the repository pattern in this application. The repository pattern is an interface. This is one of those places where I planned well. So I have to just quickly create one. Stub by earthquake service. No, it's the repository. Stub repository. We'll steal one from up here. There we go. And we pass him in to the view model. And I don't even need to put any operations on it because I really don't care. I just needed to provide a value that was legal. And that's a legal value. So now I can tick this handler. I can call it as many times as I want. Okay? And so what do we want to check? We want to check that if I call it once, refresh message gets set. And maybe before I call it once, refresh message was not set, or it's different. So let's do that. Let's do this. First message is the view model's refresh message. Then we will pump the handler, make the tick fire once, and then we'll get the second message. Okay? And now we can assert. And what we want to assert is that they're not the same. Okay? And there's our test, TEE 2012. We'll go and check our test window. Find our test in here. Oh, it failed. Why? What did I do? I know what I did. Of course, I never called start. Right? Remember, all of this happens inside of start timer. So the tick had never been set. Nothing had ever happened. So I actually have to call that as well. Oops. So we'll call start timer. Now, if we want to be truly smart, what we will do is we will assert that is not null the tick. Make sure we have a valid tick before we proceed. Okay? Now what? Not equals failure. Okay. They were the same. Because the first time through the tick, he actually still sets it to 30. We need to tick it twice. In fact, we'll do the first tick here. Because remember, my for loop went 30, 29, 28, 27. And so it said 30 the first time. And here's our test now passing. Okay? So I was able to reach in and replace that dispatch timer that somebody else created inside of their own method using that all instances capability of the shim. And it will take over dispatcher timer for the entire app domain within that bounding condition of the context. This is pretty cool stuff. We can use this in all kinds of crazy places. And I'll show you some more in just a second. I'll also show you how we can configure and tweak and control all of this stuff to our heart's content. All right. Any questions on that? Yes?
When you got all this done, it was very impressive. How happy were you with the original code? It seems like debugging the tests and stuff was 3 times as difficult as
Yeah, so the question is basically, how happy am I with this code at this point? And that, writing that test was not particularly easy. You're absolutely correct. It was not. And in fact, it required me to have internal knowledge of the system under test. By definition, this is a white box test. This test understands the implementation of what's happening on the inside. And that's kind of what I say here. No, it doesn't. But we have to have this internal awareness because I have to know what to replace. This is very challenging. This can be problematic. But sometimes you don't have a choice. So in this case, the system I was testing was my code. So in theory, it was within my power to go and fix it. But what if it was a control I bought from a vendor? I can't now. I don't have the choice to change it. Or what if it's from another team in my organization and I'm not allowed to change it? But I still need to isolate myself from it. So what I do in these cases is I pull out a decompiler. I use Telerik decompiler or Reflector or ILSpy, any of those. I pull it out, I pop it open, I read the code, and I figure out all the things I need to shim away. I don't like it. And this is why you will hear me say very regularly that you should do this because you have to, and then you should not like doing it. So, quick review then. This is runtime interception of any .NET method, and we're using the profiler to get that done. In JavaScript and Ruby, they often call this monkey patching because the language allows you to do it so easily. You can just take any method and replace it with something else on the fly. That's why you don't really need mocking frameworks in JavaScript. Sometimes people use them, and I don't really understand why, because it's just not very hard. So if you have these external components that cannot be refactored, we've got ASP.NET things, we have HTTP contexts, all these other things. This is a great place to use these. We have non-virtual methods. We have statics or constructors or sealed types, other things we need to replace. Because with shims, I can get into the constructor. I can even get into the static constructor. I can get into some very ugly places in the code. That's pretty cool. Properties I showed you. We can even get into events. And if you have legacy code or code you're not allowed to test with untestable designs, this is a great way to get the system under test. But if I return back to the catch-22, remember what I said was, we want to refactor properly. The Agilista says, refactor the code so you can test it. And we say, yeah, but I can't refactor it because I can't test it. Now you can test it. You can now create a test that pins the behavior. We call these pinning tests. It pins the behavior of the way the method is now. Pin it to the table. Now I am safe to refactor. Now, as I introduce interfaces and extract method and do all of these other things to pull it out, I know if I change the behavior because I have these shim tests that lock it down. And as I say here, but don't stop there. The right thing to do when you have the control of both sides of the code is to keep going and aim for a good design. Start doing the refactoring you need to do using the tests we created, using these shim tests in order to know that we have the behavior locked down. And now you want to be trying to use stubs or mocks, use interface separation, use interface extraction. Keep that shim test running until you're done. So that's why you'll use things like the default implementation, null object, and things like that. Keep that running because you have to know that it's still good. And then when you're done with all of your refactoring and it's all clean and isolated and solid, then you can remove the shim test. So there are a lot of interesting tips and tricks that we can do, and I'll be showing some of these in my next demo, but I just want to bring up some of them so you can think about some of the things. And some of them I've already showed you. So you saw me use a closure, right? A closure was when I collected the tick handler into a variable that was defined outside of that anonymous delegate and then was able to use it later. This is a really, really powerful technique when working with either shims or stubs. You can collect any of those variables and pull them out. And it's actually why I like to use lambda expressions for those anonymous delegates instead of another method on the class. If I put another method on the class, then the only way to share the state is by putting a field on the test class. And anytime you start to put state into your test class, you have to get a little bit worried because depending on which test framework you're using, you're not really sure when does that state get cleared, does the class get reinitialized, things like that. So I just don't ever put state in my test classes. Works a lot better. Nice and safe. When I shimmed out the system reference, it was interesting, you didn't notice it, but I will show it to you in just a second. We really only provided shims for a few things. We didn't do everything. System is dangerous. So you can imagine what might happen if perhaps I shimmed out the debugger or app domain or something else that's just core to the way either Visual Studio or your test framework or any of those things work. Or how about if I shimmed out the test framework? There's a lot of things we can do that are very ugly. And in particular, app domain and some of the core things in .NET, we do not include in the list. So we have a whitelist for the system reference. You can override it. And I'll show you that in just a second. So if you want to be scary, you can. I recommended this when I was showing you the code. I do recommend that you always declare your shim context within the test. I've done some experimenting with this. If you take your shim context, and you can do this, and I'm recommending you do not, and instead call create in your test setup, and then call dispose in your test teardown, and then store it in a field in your test, that other rule I don't like to break, it'll probably work most of the time. Again, the problem comes with whatever the test framework is doing, NUnit or XUnit or MSTest, after your method ends and before he gets around to calling the dispose. If you have done any shimming there, it's outside of your control and you may crash your test framework. I like the scoping region within my test. I also like it because it reminds me that I am doing bad things here. All right, we don't like these. I don't like them. This is a very powerful tool, but you should not like having to use them. Every time you have to use them, you should say, okay, wow, that's a design problem. But it's also a very important tool. You have to have this, or else you'll have code that you can never test. So again, my final recommendation is to, once you have the system under test, remove the shim tests by doing the correct refactorings to clean up the code. So there's a bunch of interesting little tips and tricks and some good things to know about shims that can be a lot of fun, shims and stubs and fakes. And so I'm just going to go a little bit off-road and show you some of the fun things that are useful to know as you start playing around with this. So if I come back in here into Visual Studio and we take a look, I want to show you a few things. Let me switch to the other project, because it's simpler. If we take a look here at this fakes directory, when we added our first fakes reference, this directory got added to our project, and these files got added to our project. These files are checked into your version control system. These are basically the build instructions for the creation of the fake assembly. But it's just a simple XML file, so we can take a look at what's in it. This XML file is nothing more, when it first starts out, than the name of the assembly that's being targeted. But we can put more content here. Yes, question? Yeah, so the question was, if we're using NUnit, does fakes work? Yes, and in fact, I'm using xunit.net here. I'm not even using MSTest. Right? So some of those tests I showed you are using one of the third-party frameworks. It is managed only, though, so if you're working in native C++, we don't have support for that there. But if we're in C# or VB and we're using NUnit or XUnit or MSTest, it works just fine. So there's things I can do here. Remember, we generate this assembly. We compile this assembly based on what we find in the system. Well, maybe you want to shorten that compile time down by eliminating a bunch of types that you do not want it to generate. Maybe we don't want any shims at all. We only want the stubs. So you notice we've installed the XML schema. Oops, that's not the right direction. Over here. Visual Studio comes with the XML schema for it. And so as we start editing this file, we're getting some contextual information and some help docs. So I'm just going to go to shim generation, and I'm going to disable it. So now when that assembly gets generated, it will contain no shims. It will be stubs only. So it's going to be a much smaller assembly. It will generate much faster. That's one thing we can do. We also, if we go into the stub generation section, and I'm going to create it as a child node, we can be very explicit with this add, clear, and remove which things we want to have stubbed. We can do the same thing in shims. We've got very precise control over what we want stubbed and not. So if you have a really large assembly and you're trying to generate stubs for just 4 types, you can come in here and say clear. So now the list is empty. Nothing will be stubbed. Add, type name, my type, whatever I want to put here. Okay? And if we look at the IntelliSense for this, or not. Come on. Come on. IntelliSense keeps going away. Come back. There we go. an optional filter to filter the types based on their type name. And you'll notice it takes wildcards. So we can use stars. So we can pick things up by only certain namespaces, by only certain naming patterns. We can use wildcards. Okay? So I can do type name foo star, and that will get all of those. So at this point now, I'm not going to have any shims, and I'm only going to have stubs that start with foo. That's nice. Now sometimes what will happen is you'll discover a type that isn't being shimmed properly, or it maybe fails when it shims. This does happen. There's a lot of strange things that the CLR can do, and every time we find one of those, we file a bug and fix it. But if you find one, I'm going to teach you another trick for getting some diagnostic information about the generation. If we go up here to the root node of the XML element, you'll notice we have some things we can do up here. The most interesting one to us is diagnostics and verbosity. So let me just quickly show you what happens if I do a build right now. I'll do a build, and we'll go and look in the output window. There's really nothing here. Now if I go here and turn on diagnostics is true, and verbosity is noisy, adequately descriptive. And I'm actually going to have to rebuild. Okay. Now, we don't have anything here because I have the filtering turned off in the build system. Give me all of it. So now what we got is this gigantic, ridiculous log file. But everything is in here, including all of the fakes generations. So this means we can now go and find all of the fakes instructions that are happening, and we'll get all of the definitions of what it did, all of the different types that it generates. If it fails to generate a type, if it successfully generates a type, if it fails to generate a method on a type, all of that information shows up in the log, and you can figure out exactly what's happening. Very nice when it's not generating what you think it should have generated. Makes it a lot easier also when you send me an email and say something's broken. You can then send me the log and tell me why. We can then try to reproduce it and get it fixed in our next update. So that's another good thing to know. Sometimes what I've had people ask me is, so if it's generating an assembly, I'd like to see the code that it generated. Believe it or not, you can, and I'll show you the trick. So if we go here and say show all files, we all know that we get our bin directory and our obj directory. What I'm going to do is I'm going to go into the obj directory, debug, and there's a directory called fakes. We'll look in there. And you find all of these funny folders, M, S, and SUT. Well, what we've done is we've named the folder after the project it's targeting. So M is MS Corelib, S is system, and SUT is system under test. It just uses a name that's roughly derived from the project you're taking the reference on. So if we were to go and look in system, and we dig down here a little bit, gotta find one. Oh, I know why. There we go. Here's the CS file. And if we look at this file, well, it's empty. Does anybody know why it's empty? It's empty because I changed the fakes file. I said no shims, stubs named foo. I don't have any stubs named foo. Okay, we better fix that. So we'll just go delete that stuff that I put in there. Just clear all this out. Back to where we were, which means do everything. And we'll now rebuild the system under test. We'll go and check yes, please reopen it. And boom, here we go. So now what we have, this is the actual source code of the shims and stubs. So if you want to know how this works, you can figure it out. Now there's an interesting thing in here that is for those of you who perhaps like to extend and build on top of, maybe. If we look at our stubs, let's see, it was, if we look at the stub methods in here, we're going to find it does this very interesting thing. This is the implementation of, remember our iCurrentTime provider had a method on it called now. And there's a lot of namespace ugliness happening there. But if we decompose this code just a little bit and try to figure out what all of its parts are, all of this bit here is about calling out to a user-provided observer. This is the observer pattern. And the observer pattern can be used to track and log things. So earlier when I mentioned that we're not a mock, because we don't do verification, verification requires tracking and logging. This is a hook that we can use to generate a verification framework. Just plug one directly in. Then, line 262, this line here, is the actual call to your delegate. And then we have some cleaning up. That's about it. So they're very simple. And this is why they're fast. There's really not very much code here. And all of this bit at the beginning doesn't even run unless you've installed an observer. So it's very tight. Now, if we look at a shim, there's a little less code to see because more of it happens in the profiler. And so we just have to kind of be aware of that. Find one down here. Okay. So if we look at the shims methods, you can see basically all they do is they start calling out to the runtime. And there's much less option for you to do things here. But if you were curious about how the code works, you do have access to all of the code. It's right inside of your solution space. Okay. Get back out of here. Sorry, checking for hands. Yes? How do you install the observer? Let me show you. I was hoping somebody would ask. Okay, how do we install the observer? So if we go back over to, where did I have a stub? I think I took it out of this one, didn't I? I did. This one had stubs in it. So the observer is only on the stubs and not on the shims. And if we go and take a look at one of my tests here where I can go to the bottom and we can take a look at how this works. So here is the stub. Now, the stub has on it a property. So I'm going to use the initialization syntax to let me see the properties. And here it is, instance observer. So I can install into here an observer of any kind. Okay? So maybe I'll put on there a stub observer, which already comes in the framework. But maybe we need to store that, so we'll use the closure trick again. No, let's not. Let's leave it, just to show you a trick. Okay. So we've done that. So now if you wanted to start trying to think about a verification framework, and verification is typically used when we want to confirm that the calls made on our stub were the ones that were expected. Okay? Did the call into the stub happen? Was it the correct number of times called? Did it pass the correct arguments? So all of that data should be available on our observer. Let's look and see. So if I say stub.instanceObserver dot do I have the type? I have to cast it because he doesn't know what type it is. So let's do this. So now we have access to the calls, get calls. And get calls, if you look here, returns an array of every call that happened on the stub with all of its arguments and everything. So now with just a little bit of work, we can create a verification framework that hides all of this up, and suddenly we can be actual mocks. So we don't have it in the box right now. But you can see we've done a little bit of homework to prepare ourselves for it. Should we need it later? Or should you need it now? So that's a nice little trick to know. A couple of other things that we're hiding in there, we'll just have a quick peek here. Because the tips and tricks section is always about crazy things. And then I have one last crazy to show you. So there's this thing called instance behavior. This allows you to configure what does the stub do if the user makes a call that you've not provided a delegate for. The default behavior is to return default of t for any method that returns a type, or to just do nothing. But maybe you want to be very explicit and you want to throw. Okay? So it turns out there are values you can put here. And we have a bunch of choices for you. So you can see we have behave as not implemented would do exactly what I just said. So by putting this line on the stub, what's wrong with you? So this instance behavior property is an iStub behavior, and stub behaviors are something else. Yes, sorry. I'm not sure what I'm doing wrong. I'll have to look at it. Yeah. There are a couple of different variations. Actually, this one is a method, and the reason this is a method, and I'm just typing poorly now, so forgive me. The reason this one is a method is because if I do this, all stubs now behave as not implemented. This is the global override. And there's a different enumeration I don't have the using directive in for, which allows me to plug in a very specific one. It says this stub will throw as not implemented. Okay, let me jump back to one last fun little demo that I have that is always a little scary to run. But that's what keeps conference talks interesting. Evil stuff. So let's take a look at this system right here. And suppose I wanted to test this. I'm sure you can imagine where I'm going to go. So let's look at the test. I'll set them side by side. And so I shim the directory .delete. And it says delete string Boolean because it's the delete method that takes a string and a Boolean because I said all and recursive. So yes, please actually delete all of my documents. And you can see I replaced it with a console. Nice try, but you did not delete this directory. And since it's my working directory, I actually do have the permissions to do it, so we won't even have that safety net. And let's hope I don't delete all of my presentations. There we go. And we got some output. Nice try, but you did not delete your home folder. Yay. So, like I said, you really can. I have seen somebody do this demo and mess it up. He did the other delete. There's about 4 overloads. And so he did the wrong one. And he ran the test and it passed. He didn't get his output message and his documents folder was gone because it doesn't move it to the recycle bin. So that's always kind of fun. Okay, so let me jump back over here real quick, and we'll wrap this up. So we talked about solid and how important it is. Solid is what gets you in a position to have a well-designed system and also a well-tested system. But when you do not have one, you still need to test it, if for no other reason than to refactor it. Okay? I showed you a lot of very powerful ways to use shims and how to configure it and customize it, how to understand how it works on the internals, and get deep down inside. And I'm glad Marcel even asked me to show you how to do the instance observer, because that's a really cool trick that not very many people have discovered yet, because we haven't talked about it very much yet. It's new in the RC. So you can test your design, even when you think you can't. But you should use that to influence the design and to change the code. I will be around, and here's all my contact information. I want to thank you all very much. I want you to have a wonderful rest of your last day at TechEd. And please remember to fill out your evaluations. Thank you very much. I know there's a slide that says, there you go. Please submit your evaluations.